Okay, this is the first process that we're going to look at for outcome 2 and analysis of water, gravimetric analysis. And we're going to be doing on next week a prac to work out the amount of sulfate in fertilizer. So when you look at a glass of water, you can't tell by looking at the glass of water what's in it. So we're going to be looking at a variety of techniques to work out the type of chemicals that might be in it, which is qualitative analysis, and also how much of a chemical, which is quantitative analysis. So we've looked at the fact that there are ionic compounds, salts, which are soluble. Some man who's the sea water has come in here, and the white powder is salt that they're collected, salt from sea salt. If you collect sea salt, there's lots of other ions in the sea as well. So as well as sodium chloride in here, there would be magnesium, potassium, calcium, lots of other ions. The farmers, when they fertilize their fields, plants need phosphorus and sulfur and nitrogen. It's quite often what's put in fertilizer. When it rains, this fertilizer runs into the rivers and helps grow algae as well. Algae is tiny little plants. They sit on the top of the water and block out the light and block out the oxygen and end up killing the fish. So runoff of fertilizer into waterways and into the sea is a large problem in some places. Mining is a large problem too. They often use lots of water in mines, and then they just, quite often they're not supposed to, they let the water just run into the waterways. They're mining for things like gold and silver and copper and other sorts of things, but what they dig up might be some lead or cadmium or heavy metals, and that can run into the waterways. There's lots of ways you can get ions, heavy metal ions in the water, so you need to be able to test to see what sort of ions you've got present, because drinking the water with these things is not good. I've got lots of examples. I should have stopped actually. Shellfish, they feed by kind of sucking the water through them to get all the any nutrients in the water out, but as well as getting nutrients, they can be collecting heavy metals in them. So if the water's polluted, then eating shellfish is not a good idea because they're filter feeders. Okay, as well as ionic compounds dissolving, polar molecules can dissolve. So a glass of water might not be all water. A vodka is actually 40% ethanol molecules. Yeah, so, most of the glass is ethanol molecules, or sorry, 40% of the glass. Sugar is a polar molecule. Forms hydrogen bonds with all these hydroxyl groups. So a glass of water could be full of sugar too. Alright, so you need to write down what qualitative is. Qualitative is at working out which chemicals are present, and quantitative is going to be working out how much. So this is our first quantitative technique that we're looking at, gravimetric analysis. We're going to do volumetric analysis and spectroscopy and chromatography in year 11. We'll do these two sorts of spectroscopy. These ones are quantitative. They tell you how much, and these ones are qualitative. In year 12, we're going to do redox as well, infrared, NMR, and mass spec, and we're going to go back over chromatography again and volumetric analysis, acid and base. So in year 12, we don't do gravimetric, AAS, or UVVs. We only do those in year 11. Okay, so gravimetric is based around gravity. You've got some sort of ion dissolved, or an ion in like in a shellfish or whatever, fertilizer or whatever you're studying. and we want to know how much we've got. So we're going to dissolve everything, and then we're going to add another ion to it, which will make it precipitate. So we have to get our precipitate away from everything else. It'll settle to the bottom. Then we can weigh our precipitate, and using stoichiometry we can work out the ion that we're interested in, or the salt that we're interested in. So if we were interested in hydroxide ions from something, we could add lead to it, precipitate. The lead would drag the hydroxide down to the bottom, form a powder, and we could measure how much hydroxide we had because we could measure how much lead hydroxide we had. Okay, these ions, this is soluble floating around, and this is soluble floating around. When we put them together, these form the precipitate, but the potassium and the nitrate are still soluble. They are spectators, they haven't done anything. So I've introduced to some of you that these are spectator ions, but people who are away on Friday, yep, need to know what spectator ions are. So ionic equations are just the ions that form the precipitate. When you write an ionic equation with these ions, you have to show the charges, and then when you need to make sure that it's balanced too, just like other reactions. All right, so we can't use this technique. That's why they're not doing it in Year 12 anymore. It's a bit limited. You can only study a few things. Like study how much phosphorus was in something, or how much sodium, well, how much chlorine is in something. But it's a little bit limited with what we can study. You've got these in your book. Which ions are soluble? All right, so the example we're going to do, oh, sorry, I keep touching them. The example we're going to do is with peanut butter. So it could be with anything. If you wanted to know what percentage of whatever it was salt, you know, how salty your food is, you could use this technique. So what we're going to do is we're going to work out a percentage, which means that we need a sample. So if we had 100 grams of this peanut butter, we're going to work out what percentage of it is sodium chloride. So we need to weigh our peanut butter sample, because that's going to be the number that we'll put on the bottom to work out the percentage. We're going to blend it, like mix it up with water and dissolve it. And then because we're settling, we're going to dissolve it so that the chlorine ions are floating around. And then we're going to trap those chlorine ions by adding silver to make silver chloride precipitate. So because we're going to weigh the silver chloride precipitate, we don't want other solid parts in there to add to our weight, so we have to filter them out to start with. So you put it through a filter funnel, you collect like the bits of peanut that haven't dissolved, and this sodium chloride that's dissolved, we collect the solution. Then we add an excess of silver nitrate, or silver something. Nitrates are always soluble, so silver nitrate would be fine. The silver will get with the chlorine and make silver chloride. So we want to collect that and weigh it, so we have to filter it again. So this time we're collecting what's in the filter paper, and everything else goes through. So some of the things that might go through would be the sodium ions that haven't been precipitated, and the nitrate ions, but there'd be lots of other ions in peanut butter. We want to make sure that the silver ions and the nitrate ions and whatever else have definitely gone through, so we're going to wash it with water. And then because it's wet, we're going to have to dry it in an oven, because we don't want to weigh the water as well. And then we weigh the silver chloride. So to make sure it's definitely dry, we would repeat it, put it back in the oven and weigh it again. So if the weight dropped, it means it was still wet. So we have to dry it again and keep doing that, drying and checking and drying and checking until the weight stayed the same. So we say that we're doing it until we have a constant mass, heating until constant mass. And then you know that it's definitely dry. Alright, so this is a picture showing the kind of steps that we're talking about. It's missing quite a few of the steps, so this is in your book. So first of all, we're weighing our sample of peanut butter. Does that look like peanut butter? No. Okay, and it's totally missed out the fact that you filter out all the chunky bits and dissolve it in water, and then we add our silver nitrate to form silver chloride. And then we're going to filter it through this fancy kind of filter setup and collect the silver chloride. Then we're going to wash everything else off, dry it out, and then weigh the silver chloride. Okay, let's do an example with numbers. So, the silver chloride precipitate collected from a 7.8 gram sample of peanut butter has a mass of that. Okay, so in these things you're going to have two masses that are given all the time, and you need to make sure that you don't accidentally use the wrong mass, the wrong spot. So this mass is the mass of peanut butter that we use at the end to work out our percentage of salt. This is the mass of the silver chloride. Okay, that's what we need to use to work out the amount of salt, sodium chloride that we've got. So the first thing whenever you're doing stoichiometry is to write out the equation. I think writing the equation might help you understand what we're doing. So we've got some salt in the peanut butter, we dissolve it, we add the silver to the chlorine that's floating around and get silver chloride. Okay, and then we're going to have to wash off the sodium ions and the nitrate ions and whatever other ions so that we've only got silver chloride. Alright, so the mass of silver chloride, the mass of the precipitate is that, and the mass of the peanut butter is the other one. So we're going to use this mass to work out the number of moles, and then we're going to use the number of moles of that to work out the number of moles of this, and then we'll work out the mass, and then we work out the percentage. Alright, so the first step, find the number of moles. Once we've got the mass, to work out the percentage, we need the mass of the peanut butter, this, and whatever mass of salt that we had, and then we can work it out. So if this mass is 7.8, if we have 7.8 grams of salt, then it was 100% salt. Okay, if we have 3.5 or no, 3.401, no, what am I doing? Anyway, you get the idea. Alright, calculate the amount in mole of silver chloride precipitate. So number of moles is mass over molar mass. Look at this, I'll cut this out of the book. They're not putting their equal signs one underneath the other. Okay, so that's the mass of silver chloride, this is the molar mass, and that's the number of moles we've got of silver chloride. So next one, stoichiometry, ratios. So it was all a 1-to-1, which makes it really easy. The number of moles of silver chloride this is what we want. The salt, that's what we've got, it's a 1-to-1. So if I take that over the other side, I've got 1 on 1, same number basically. So the number of moles of silver chloride is the number of moles of sodium chloride is the number of moles of silver chloride, equals the same thing. I should have that equals underneath. Calculate the mass of salt. So now we've got the moles. We rearrange the equation to get the mass. Make sure you're rearranging your equation properly. So we've got 0.0457 grams of salt. Calculate the percentage. So it's the mass of the salt divided by the mass of the peanut butter. So it's 0.5857%. They should have done their significant figures properly. This is 0.057, 3 significant figures. So if we round that up, it would be 0.586% salt. Alright, the main reason that we're doing a prac is that when you get to do experiments in Year 12, you need to be able to explain any mistakes that have been made, any errors that are possible. So we go through step by step. We had to weigh the peanut butter sample, blend it up with water, so dissolve it, and filter out any undissolved parts. So, things that might go wrong. If less peanut butter was weighed out than was recorded, so you wrote down that you had 7.802, but you actually didn't end up putting that mass, dissolving it all. So maybe you moved that from that container into a different container, the container you used to weigh it out. You put it in scraped it off and put it in a different container, and you didn't scrape it all out, and you left some behind. So you would work out your salt then that you would be dissolving would be less. There would be less salt in there because you'd left some peanut butter. So less sodium chloride, less silver chloride precipitated, less sodium chloride calculated. So the mass on the top of your here would be too low. So your percent, this fraction would be smaller. So your percent would be too low. Okay, if it wasn't filtered properly and undissolved parts remained, so you had a bit of chunky stuff, some peanuts or whatever, in sitting on the bottom, you're going to filter out your precipitate and the peanut goes with it. So then, therefore, the mass of your silver chloride that you're weighing would be too high, so the mass of salt calculated would be too high and the percentage would be too high. Alright, so this should be peanut butter. We dissolve it, which they haven't shown, and then we're going to use a piece of glassware to add our, so we've put the salt that's dissolved from the peanut butter and everything else in here, and we're going to add our silver nitrate from this apparatus. When the silver and the chlorine start to collect together to make the precipitate, to make the little solid, the crystal, other ions can get trapped in that. So you could get some sodium ions trapped or some nitrate ions trapped, and then they would be trapped in here when we collected it, and then when we weighed it, so it would make it too heavy. So in order to kind of stop that happening, if we put this whole thing on a hot plate and heat it the whole time, it's getting agitated, and if you've collected other ions in there, the crystal or the salt that you're forming is not very stable with other ions. Only the silver and the chlorine collect. So if you've got sodium stuck in there, it will break up. So if you heat it, it helps it break up and release the sodium ions and nitrate ions, whatever else that you've got. So we need to add an excess. Excess means too much silver nitrate to make sure that we've got enough silver to precipitate all of the chlorine ions. So if you didn't do that, if you didn't add heaps of silver nitrate, then maybe not all the chlorine ions would precipitate. So you'd have some chlorine ions with no silver attached to them, and when you washed it all through, those chlorine ions would wash through. They wouldn't stay in the salt. So your silver chloride would be too low, so your salt would be too low, so your percentage would be too low. The boiling I was talking about before, if you didn't do the boiling and helped try and break up your silver chloride combination so that any other ions that were trapped in there were released, then you would have these other ions trapped in there and you would be weighing them, and so the silver chloride would be too heavy. Filter and collect the white precipitate. This thing here has a filter paper on it, and it's such a fine filter paper to collect this really, really fine powder that we're silver chloride that we're collecting. It's so fine that you can't just put the water on here and expect it to drip through. It would drip through really, really slowly. We would be there for days. So we're going to put a tube on here and attach it to a tap and run water through it, which makes a vacuum. It's like sucking the air out of here, and that will suck it through. So because you're doing that fairly forcefully, some of the silver chloride can get around the filter paper, and you would lose it in here. So if if we filter it, and this is one of the main errors that happen, you can lose the silver chloride around the filter paper. Probably a couple of groups that will happen too. Okay, so after you've filtered it, you might have some sodium ions that are sitting on the top, attracted to the chlorine there, or you might have some nitrate ions attracted to the silver, other things stuck onto it. So we want to wash them through because they're just loosely sitting there. They're not properly bound. So if we get some hot water, that helps, give it some energy to break it up and wash it through. So if we didn't do that, then you'd have other ions sitting on there, which would make the silver chloride higher, the mass, than when we weigh it. Makes the sodium chloride higher, makes the percentage higher. So after we've washed it, it's wet. If we weighed it then, it would be too high. So we're going to put it in an oven and dry it out. So on the third time, after it's been drying, then we'll come back. If it wasn't dried properly, then the weight would be too high. So first, we have to weigh the precipitate, the silver chloride. We get the chlorine ions. So for every one of those, we would have had one of those, and we get one of those from here. So the amount of this equals the amount of that. So to find the percent, we're assuming we're using this to indicate this. So we're assuming that all the chlorine ions came from sodium chloride, from salt. It's not necessarily true. In the peanut butter, maybe there could be potassium chloride or calcium chloride, or some other sort of chlorine. So the assumption is that the chlorine that you're measuring has all come from sodium chloride. All right, so there were three things that made the weight go up that we've gone through. Made it appear that there was more salt than there actually was, three errors. So if we didn't filter it properly, then there could be peanuts in the silver chloride precipitate. Some of the other ions, if we didn't wash it off properly, they could be still stuck there and they would make it be heavier. And if we didn't dry it properly. There was also three errors to make less salt, lower percentage. When we originally filtered it, some of it might have been lost, so we weren't weighing all the salt that potentially could have been there. When the precipitate was being formed, not enough silver was added, so not all of the chlorine was collected. And when we were filtering it, we might have lost some underneath the filter paper. This may or may not make sense to you at the moment, but hopefully if you've gone through this, when we actually start doing it, you can kind of picture what's going on. Okay,